So what I want to share with you is some of the research we're doing at Senseable City Lab, but also how we try to turn it into things in the real world, into startup or into projects. And I remember actually an email that came from our previous president, from Raphael Reif, that was probably 3 or 4 years ago, where he said, at MIT, we want to do the best possible research, but also making sure that it has an impact in the world. In order to do it, then, we cannot just publish in scientific journals, we actually need to do something else. And so that's, why I'm grateful, very grateful to all the things we've been doing over the years with TLO. And also you see here some of the other ways, maybe our design office or other ways to turn research into projects. Now, first of all, what we're doing is looking at cities. But when you look at cities in the future, there's a few interesting epistemological questions. So, for instance, let me show you how people looked at the future in the past. So what you see here is actually a few drawings that were done at the beginning of the past century, between 1899 and 1910, where people imagined life in the year 2000. And in some cases, they actually got it right. For instance, they saw mechanization in agriculture coming, as you see it here. At the time, they even imagined Roomba, the little robot, actually a TLO patent, developed by our colleagues here at MIT, Rod Brooks and others. That's how they saw it in the early 20th century. But in other cases, they actually didn't get the right future. They got it wrong. They would think that today we would move through the planet using whale buses, or that the police would actually patrol Cambridge, Massachusetts in this way. So even if with your wildest drone fantasies, you wouldn't imagine this happening yet. So what I'm making here, the point I'm making here is a point that was beautifully made by Karl Popper, the great philosopher, is the future is open, it is not predetermined, and thus cannot be predicted except by accident. So the possibilities that lie in the future are infinite. And so what is the way actually to look at the future, and especially urban futures, what we are looking at the lab? Well, the best way probably to do that is to look at design. And again, this is the last quote I'm using today, but this is by Herb Simon. As you all know, Herb Simon got the Nobel Prize in the past century. He was an amazing mathematician and scholar and researcher and so on. In a great book called The Sciences of the Artificial, actually, MIT Press book from the 60s, he says the natural sciences are concerned with how things are. Design, on the other hand, is concerned with how things ought to be. So design is a way to explore the present and turn it into something else. It's not about predicting the future, it's about looking at the present and how we can design it and transform it, turn the present into something else. Well, that's what we do at the lab. We do it at the scale of cities. We're passionate about cities. I see a few people from the lab here in the room. But cities, for different reasons, cities are very important when you look at the sustainability of the planet. Incidentally, this is what we will explore in 2025 at the Venice Biennale that I've been just asked to curate. But also cities are interesting because thanks to the convergence of digital and physical, so thanks to bits and atoms coming together, then it's the way we understand cities, we can design them, is changing in a very radical way. And actually, I remember when I came to MIT, I was here at the Media Lab, I was just upstairs with Hiroshi. That was the beginning, 20 years ago, the beginning of the convergence between digital and physical. And, that is now everywhere, and is changing, again, the way we can understand, design, and ultimately live in cities. So today, I wanted to share with you some of the projects we do. And then, in the middle of the research, I would add also a few examples of how the research made it into the real world in different ways. Well, I decided to start from one of the first projects we did. This was 2006, almost 20 years ago. At the time, this was the Venice Biennale. Venice Biennale is a big exhibition about art and architecture every couple of years in Venice. 2025 will be again architecture. Hashim, our dean, curated Biennale 2 years ago, as you might know. And what we did here in 2006 was actually, for the first time, take a city and use data from cell phones, from millions of people, to see how a city lives. That had never been done at the time. So what we did, it was being exhibited in Venice, so we decided to focus on an Italian city. We picked Rome, the capital. We got the data from Rome, data from cell phone, from taxis, from buses, and so on. In real time, we sent it to MIT, here to the Media Lab, with a number of servers we set up at the time, kind of a proto cloud. And then we analyze it, we visualize it, and we sent it back in real time, near real time to Italy. So now we started collecting data such as this. This is actually a very special day when Italy won the soccer World Cup. In 2006, that's the city of Rome. You see the Colosseum, the river, before the match. And people moving here and there in the city. In the moment the match begins, you'll see it, and silence. Nobody talks anymore. And then France scores. Italy was playing France. Italy scores, halftime. People make a call. And then in the normal time, first overtime, second overtime, a famous headbutt by Zidane. And then finally, Italy wins. And then everybody starts to move around and move in different parts of the city and so on. But that was the first time ever actually to use this data for to look at the city in real time. And without the data, we'd not have been able to look in the following years at different things. This paper from a few years ago actually was possible because we took some of the data, similar data to the one you saw, for tens of millions of people. And we discovered something interesting. I will not get into the details, but basically there's an old law of human mobility that shows that if you take two cities, say Boston and New York, and you want to look at the flows between the two cities, they follow some kind of gravity law. So population 1, population 2 divided by a distance power alpha, where alpha is an exponent between 1 and 2. Well, at the time, people could only look at the total flows, but with cell phone data, you can look at how people, not only at distances, but frequencies, how many times people go back to the same place. And when you look at that, you find it beautiful. Actually, you get a beautiful collapse on one single curve. What is very important is not only distance, is distance times frequency. So actually, we discovered this kind of frequency dependency that we've not been able to see without this type of new data we started experimenting with 20 years ago. Another little thing is something that puzzled me since I was a student at Cambridge. This was the college I was in, so Darwin College. And when I was at Darwin, I discovered something that I found very disturbing. And the fact was that I was living here, and I was going to my department, like every student in Cambridge. But I was following one route to go from A to B, from the college to the department, and a different route from going to the department to the college. And that really puzzled me, because if you study shortest path is symmetrical. So if your brain thinks shortest path, A to B is equal B to A. So why the hell I was following? The probability was higher that I would go one way, A to B, in a different way, B to A. And so somehow you could say I was consistently inconsistent. And again, I was very puzzled by this finding. Well, it took us quite a bit of time, but now with data analyzing, in this case, in this paper from last year, analyzing hundreds of thousands of people, both in Cambridge, in Boston, and in San Francisco, we actually saw this is something we all do. Our brain, like the brain of animals, is not coded for shortest path. It's actually coded for something we call here, we define here, pointiest path. Or if you want, well, people, this was together with Josh in brain and cognitive sciences and his team, but basically what with animals people call vector-based navigation. So our brain tries to look at the vector where we want to go and try to minimize angular deviation from where we want to go. And if you look at that, then it's not the shortest path. It's good enough, it's not that different, but that actually leads you to something which is not symmetrical. A to B can be different than B to A. And it is interesting, if you think about this, it's interesting for two reasons, I think. First is that because we are becoming more and more hybrid systems, so we follow a lot our machines when we navigate. And then if this follows shortest path and our brain is coded for something different, then there's a disconnect. So as we couple more and more artificial and human intelligence, we need to understand how both of them work. But the other thing is that this is probably an interesting way our brain evolved, because if you think about the shortest path is quite computationally intensive. Well, if you look at the pointiest path, it's very easy to compute, is not perfect, but it's good enough, and maybe it saves a bit of brain power, so that a few tens of thousands of years ago, when all of us, when our ancestors were in the savannah, you can look at a lion or other dangers on the way. So it's very interesting about how our brain evolved. But other thing you can do with this type of data from the city, when you look at this, is actually taxi, similar data, not cell phone, but taxi from GPS, pickups, and drop-offs. Which place is this in New York? People from the lab can, there's a few people from the lab, so anybody, any ideas? Yes, I heard of JFK. But anyway, this is JFK. So if you landed at JFK, you were one of the little dots, a pickup in yellow or a drop-off in blue. If you look at this, it's actually the same image. JFK is down there. You see all of Manhattan and all the boroughs. If you look at the map in detail, by the way, you don't see, there's no roads. The roads just emerge because of the sheer density of pickups and drop-offs. What you see here is actually just black with water in gray, and then what you see, the structure of the city is simply the result of all the activity that happens in it. And then in this case, this is quite an old paper. It's a paper, we looked at this, started looking at this over 10 years ago. We started asking a question. Again, this question was inspired by something I think all of you have experienced. You are in New York, you are in a hotel, you're there with your trolley in the morning, you're going to the airport, to JFK, and next to you there's somebody else with a trolley. They're also going to the airport. You could have shared a taxi, but you simply didn't know. So we wanted to quantify how many trips we could share in New York between people. And if you look at this, for instance, between those 2 points in Manhattan, but any 2 points in Manhattan, you got hundreds of thousands of trips over the course of the year. This means you have thousands of trips every day, which means potentially a lot of trips could be shared by two people going more or less in the same directions. Well, we looked at the problem. We got all the data from the city of New York. Incidentally, the data was made accessible by Mike Bloomberg when he was mayor. I remember in his office at City Hall, Mike had a sign that said, "In God we trust, everybody else bring data." And so what he did in City Hall was actually force his people to share as much data as possible, including the data we got for this project. Now, when you look at this, if you are, a lot of you probably are engineers, you might think I can look at this with linear programming, but linear programming fails to look at how many trips you can share. Linear programming fails when you got so much data. So together with Paolo, together with Steven Strogas, who's a mathematician, you might know Steven is at Cornell. He's one of the fathers of modern network science. We say, why don't we develop a new way to actually look at this kind of big data sets, how we can analyze it. And we developed this system that is widely used today in many mobility problems called shareability networks. I will not get into the detail, but use network science. What you see here, those networks, they densify if you allow for a longer delay in arrival. So how do you frame it mathematically? Mathematically, you frame it like you see here in the upper left graph. On the x-axis, you got the delay, because clearly if you pick two people, they go more or less in the same direction, you introduce a small delay. But then we look at, even with a small delay, which is what you see, which is that's in seconds, so 1, 2, or 3 minutes, then you can share a lot of rides. And it turns out that with a delay of maximum 3 minutes, you could cut fleets in New York by 40%. Something interesting happened, and here I'll get back to this point, the fact that, how do you turn research into something that has an impact? Yes, sometimes you do a startup. I will show some examples of that. We've done quite a few with patents filed at MIT with TLO. But in other cases, maybe you just inspire somebody. So when we did this, we published it, we did a website, and a conversation started. And that's always good. Conversation is like feedback loop. The New York Times did the review of the results. There was an article. Nick Fox, the science editor for the New York Times, wrote a great article, but he said, yes, all of this is good, but New Yorkers really don't want to share anything. It turns out that was not the case, because a few months later we got a call from Uber. It turns out the founder of Uber had seen the paper, and we did a first collaboration between MIT and Uber, signed here not by TLO, by OSP at the time. And we started working with Uber, and as you might know, Uber Pool is what today does that. Uber Pool, now called Uber Share, allows people going more or less in the same direction to share a ride. And that has turned into quite a big, how do you call it? A big product, not only for Uber, but for many other companies, for Didi in China, for Grab in Southeast Asia, for Ola, for Via, and so on. So somehow, sometimes it's enough to do research, and then that can trickle down into the real world. If you want, we can talk about Uber Pool, Uber Share. At the beginning, I was very excited, because if you combine 2 trips into one, it means one less car on the road, which means less congestion, less pollution, less emissions in our cities. It turned out a bit differently because if you lower prices, it also means you're taking people out of the subway or the bike and you're bringing them into the car. And I wrote an article about that in the San Francisco Chronicle last year, really saying that unintended consequences should always be looked at. Somehow at the beginning we thought we were doing something good to make our cities more sustainable. In the end, the story turned out a bit different. But anyway, we look at this, we look at shareability around cities. At the beginning is this only New York? Does it apply everywhere? So we looked at data from cities all over the world. Here, if you want, there's some of the results inside. I put just the first page of the papers. You can feel free to look at them. They're all on the website, on our website. With the same data, we also look at something else. So before it was about looking at how many trips could be shared. In this case, we look at the same data for another problem. In the future, if you think of future with a lot of autonomous cars, well, what is the most important thing? Is dispatching. How do you assign people to trips, people to cars? And so here we asked the question mathematically, what is the minimum fleet to keep Manhattan on the move? Here is a little video. Could we have the audio? They say they had somebody there still? Yes. Could we have the audio?
Give us 1 second.
Oh, yes. Anyway, so here you see the data. That's real data from New York with all the taxis. And then today, a lot of them are empty because just move around empty, waiting to pick somebody. And then what we did is found this kind of optimal algorithm, again, based on shareability networks, that you see here how it works. And if you do that just by optimizing that, you could actually cut down a lot the number of taxis. You see it here. So today you got 5,800. If you just were to optimize the way to do dispatching, you could actually cut it down to, 8,400 to 5,400 in the future, even more with systems with potentially autonomous vehicles. Let's see if we can fix the
Just 1 second.
audio, just because later we have more videos. Or I'll continue. Or should we?
Yeah, if you can just hold for 1 second. Let us just get this set to the right.
Yeah, let's just do this. I keep on playing this, so. You want to see this?
Yeah, if you can just pause it for 1 second.
It should be. Okay.
Sorry, I need to see the audio setting.
Yeah, they're here. But they should be the right one.
Just double check with these.
Because he said that he could hear them.
Yeah, but I need to double check.
Oh, sorry. Where the hell is that?
Low-tech solution, an easy way to do this is deploy this.
This one? Or do you want the left?
We can
Yeah.
just put the left, just unplug it from that, and we're just gonna mic your speaker.
Okay.
This is the,
Sure, I know.
put that right like that. Turn this on.
Okay. Thank you. We got a low-tech solution, but we'll use a mic to do it. Thank you. All right. So again, if you want to look at the mathematics and so on, the paper is here. You can get it on the lab. And actually, out of that, again, I'm making some example. That was also a patent filed with TLO, and there's a company that's trying to turn this into kind of a way to optimize mobility in cities. Many other things we've been looking at. We've been looking at parking. If you think about the future with self-driving cars, this might not happen. The reason today, today we got, if you think about a car, our car is parked 95% of the time. It's used only 5% of the time. But again, in the future, where you got autonomous cars, you could actually reduce the number of parking spots. This is Singapore today with 1.4 million parking spots. But actually, if you don't need to park the car all the time, the car can be used by you and then somebody else in your family or anybody else in the city can be shared. Then you can look at how this could be optimized. So some of the other research we are doing, again, looking at upper bounds and lower bounds in how we run our cities. Or we're looking also at things related to how we manage other types of traffic. For instance, that's a well-known traffic light. And traffic lights arrive on our roads when cars arrive on our roads. But if you got an intelligent system where every car knows where it is and where all the other cars are, you don't need to stop anymore. You can keep on going. By the way, I think that this has stopped working.
Yep, I'm on it.
Can you all hear me? I mean, I'm speaking a bit louder, but yeah, okay. Okay. I'll continue, but then we'll see. So you can keep on going, just avoid, yes, okay. So now I'll speak a bit softer, thank you. So you can keep on going, just avoiding collisions like this. Now, don't try it yet. You know, I showed this a few years ago in the city of Naples in Italy, and they told me, so what is new here? Well, I'm Italian, so I'm allowed to make such politically incorrect jokes, but I need to tell you the former Italian minister once said that in Milan, traffic lights are instructions, in Rome, they're suggestions, in Naples, they are Christmas decorations. So I've got corroborating evidence for my statement. Again, if you look at this, it's a beautiful mathematical problem. You can look at this like a queuing theory problem. This is what we've done, and here is the paper. Again, and you can look at how to expand it. Now, at the same time, when you look at all of this, how you program the city, you also have opportunity for design. And again, our design office is in New York, in Turin, in London. And what we've been doing, for instance, been working with Google a few years ago, where we looked at the road and say, well, think about a system with self-driving cars, how the road can be used for cars, at the beginning, in the morning when you got a lot of traffic, and then midday could become something like this. Or we also won a big competition in Paris called Réinventer le périphérique, reinventing the périphérique, the ring road around Paris. In order to think about in 2050, you can think about a road that, thanks to intelligence, can be dynamically allocated in different ways. It can also be a road to produce energy. This is now starting to happen. You can put photovoltaic. We need space for photovoltaics. Instead of using green fields, we can actually use asphalt. It's a bit more difficult, but it's already happening. Or basically how we can actually bridge two sides of the city, kept separated by this infrastructure, when the infrastructure becomes safer with AVs and also cleaner through EVs, electric vehicles. So that's a little bit of the research we're doing in the lab. And as you see, we try to do the best possible research we can, but also turn it into other projects or companies, or just, sometimes just simply to do something that starts a debate, and then people these ideas can trickle down into real cities, as it happened in the case of Uberpool, Ubershare. Now, I'll go a bit faster now, but a few other chapters. One is about society. With all this data, we can understand society much better. We started by looking at communities. This was a few years ago. This was Belgium. Here we actually look at this gravity law and how it happens also when you look at how much people talk to each other. In this case, we looked at communities in the UK. At the time, this was the largest ever social network ever made with data from BT, from British Telecom, and we use it in order to actually understand communities, talking to the government, to the Prime Minister's office, in order to redesign constituencies. That would actually be something very interesting in this country, where actually the election system is still something quite outdated. It actually creates a lot of distortion. In that case, by looking at communities, we can start to look at how people naturally aggregate over space and not as something that comes from politics or from history. So, this is a mathematical question. I'll go a bit fast. You see the different communities you can get. There's a video in a moment that shows you how this happens. So every time you got a call, you create a connection between 2 points, and then you aggregate all of this at the scale of the country. You got this kind of human network. And then you use it as a beginning in order to better understand communities and how they organize over space. So from there, in recent years, we've been looking a lot at segregation, actually how communities, also in cities. In cities, traditionally in cities in the past, people had ghettos. Ghetto is a name that comes from Venice. There was a neighborhood called ghetto, where actually Jewish people had to stay and couldn't get out of the ghetto during the night. Luckily, since hundreds of years, we don't have ghettos as physical ghettos, but there's still a lot of ghettoization in our cities. And so actually we can use data, as you see in this paper, in order to look at big data, in order to see this kind of invisible fault line in our cities. And when we see them, we can then put in action different ways to bridge this kind of fault lines. And we've also been looking at what's happening with COVID. And this is actually an article, this is not a scientific article, it's an op-ed for the Times. I'm showing it because I think writing for newspaper is also a good way to start a conversation. As I said before, what happened in New York with sharing started with a debate in the city. And also, sometimes people in academia think, there's only one solution, but what you want to do really is actually to share things with citizens, and then you start a conversation. Actually, sometimes the feedback you get is positive, sometimes it's negative. I think that actually our goal as scientists is not to try to see how we should design cities, but actually how we might propose different ways to transform our cities, but then see what works, what doesn't work, let those decisions to citizens. It should be all of us together to decide what type of city we want. And solutions in one part of the world might be very different than in another one. So it depends on the local condition and what people might want. So I think that writing for for newspaper is also an interesting thing. And that's why I've been doing this often when there's a new scientific paper, to try to share the results and actually get feedback. Sometimes I enjoy very much reading the comment section. Sometimes people disagree, but sometimes you learn a lot about how the research we do can have an impact in one way or in a way that you hadn't expected before. So in this paper, we actually look at the fact that in New York, it is with Ed Glazer, who is the head of economics at Harvard, and this was a few months ago, last year. And we look at the fact that after COVID, there's a lot of empty space in New York. Actually, vacancies continue to climb. They're at the highest point, even higher than after the financial crisis. And so we actually have been using a lot of big data in order to see what's happening. We started a few years ago. We were looking at the MIT campus. Initially we started looking at Wi-Fi data and looking at the changes happening. The campus, how people went to all computer rooms to work in a new way that has happened in society at large. We used to work like this. That's actually Jacques Tati in the movie Playtime. And now we work like this. That's actually a design from our office. It's one of the largest co-working places in Europe. So initially we started looking at data from the campus, from Wi-Fi. You see it here. You see how people move on campus. This was done all with ISNT. It's always great, to work with with different departments at MIT. In this case, with people running the network. This is, for instance, the heartbeat of MIT. What you see here, you see Monday, Tuesday, Wednesday, so the days of the week on the x-axis. At the top, you see the overall heartbeat. You see people getting to campus around 9 or 10. A few people leaving at 5 p.m. A lot of people keep working till late at night. A lot of activities still in the middle of the night. And that happens on Monday, on Tuesday, on Wednesday, on Thursday. Not on Friday. Like all over the world, activity slips away quickly on Friday afternoon. But then Saturday and Sunday are almost two normal days. You remove the 9 to 5 people, and then it's almost like 2 normal days. But actually something interesting, you see on Sunday night at 10 p.m., there's a little dent. You see it there. And that's when you think, oh my God, tomorrow is Monday again. And you go back to the computer to do the things you haven't done before the beginning of the new week. But if you look at this, you can actually look at every space on campus. You can look at its signature, how it's been used over time, that you can analyze it, this is simple Fourier transform and so on. And with COVID, something funny happened. Something interesting happened because for 2 years we've been going with back and forth with COIS, as you know, the ERB, Ethical Review Board, in order to get access not only to the data from Wi-Fi, but also to the anonymized email network. Anonymizing means we don't know anything about the content or the people exchanging emails, but we got a network and we know the intensity of the links. In just a few months, before COVID, we got access to the data after we ran all the anonymization processes and so on. Well, and then COVID came. COVID came in, this is actually 2020. COVID led to lockdown on the 23rd of March, 2020. And that became the experiment that you can never do in the social sciences. You take a variable, you remove it fully, and 2 years later, you actually put it back. So you see the impact of physical space in this case, on how we connect with each other. Just if you look at the network, this was MIT before COVID. this is how it looked. You just take the network, you visualize it, and you see, the different departments and the connections between them. Then COVID arose, even without doing any analysis, just by visualizing this. This is done by one of those software based on springs that allow you to visualize a network. And then lockdown, just if you look at it, is very different. So what changed? And we started looking at many things. And we couldn't find anything. We were looking at, the number of nodes is the same, the structure seems to be the same, information, the speed of information, if you do percolation analysis, all seem to be the same. But finally, we actually found something that changed in a dramatic way. To tell you what changed, I need to go back a little bit and tell you about something that sociologists have been studying since the 1970s. Think about all your friends. Well, if you classify them, you can put them in two buckets, weak ties and strong ties. Weak ties are friends who are not friends of your friends. Here they are orange. And so they're basically links to another community. Strong ties is just a definition, are friends who are also friends of your friends. If you draw them on a piece of paper, they are a triangle, as you see there. And then there's a definition that was, just a simple definition. If you think about all your friends, you can classify them either strong ties or weak ties. There's nothing in between. Somebody who's not friend of other friends is a weak tie. Somebody who's also friend of other friends is not, is a strong tie. And then in 1973, a famous sociologist called Mark Granovetter, who's still a professor at Stanford, discovered something important. In a seminal paper called The Strength of Weak Ties, the basic weak ties are very important. Strong ties, if you look at strong ties, information goes around in circles. We tend to repeat to each other always the same information. I talk to A talks to B, and B talks to C, to me again, and the information, we don't get exposed to much information. But weak ties usually are the most important ones for creativity, for challenging our preconceptions, for creating a very solid network. And well, now you understood what I'm going to. By analyzing this, this is a paper that came out a couple of years ago, or last year, not 2 years ago, so a year and a half ago, that basically when you remove physical space, then weak ties disappear. And if you look at this, this is the graph on the paper, you see the number of new weak ties, it goes down 80% as soon as the MIT campus goes into lockdown. The line is 23rd of March 2020, but actually 2 weeks before, people started showing up much less on campus, so you see it starts going down, and then it goes down at 20%. If you look at the paper, then you see that after the campus opens up again, then it bounces back. So if you look at this, it's almost like a brain shrinking, where all the important connections in our social networks start to disappear. And so we've been using this information, for instance, to design new spaces. That's a new museum we designed in Italy, where we designed the place to facilitate encounters. We won a number of prizes, facilitate encounters, and allow people to create weak ties. This is a new campus at the University of Milan, where actually the whole campus is based on having what we call a common ground, a place, again, for people to encounter. If you need to go to an office just to stay in your cubicle, you can work from home. But then physical space creates, if it has this function of creating weak ties, then it's something we can design in a better way to turbocharge its social function. This is a new skyscraper we just finished in Singapore together with Big, where actually the middle of the skyscraper is a big plaza suspended over the city. So again, it becomes a place for people in offices and in service apartments to come together to work outdoors without air conditioning, but also to enjoy each other's company. And last year, we also created a fund. We thought, so if this is what is happening, then it means that offices will be back. Different, probably redesigned, new places, but physical space is very important. I think it's important, the fact you all came here today, there's a bunch of people connected online, but I think it's important, again, because by coming here, we can have a more meaningful conversation. You might meet other people just in the room, and that's the physical space is still important. Maybe we will not go to the office every day of the week, but still the office has an important function, a social function. And so we created this fund where we are just buying old offices and trying to turn it into something else. There's financial value there, but for us, there's urban value there, social value there. because then we take a city, a dead city, but think about what's happening in San Francisco, and we turn that into something else. We bought recently the headquarters of Vodafone in London, and we are again converting it. They're staying, but we're adding more people. So using this as a way to accelerate change. Again, we had never done this, but we decided to do it with because it's another way to explore, another channel to explore how you can take research and then bring it into actual change in the city. It's not just writing the paper in Nature Computational Science or whatever, but it's actually turning that into change, in enacting change in our cities. 2 final chapters. Autonomy. We're working out of autonomy at the lab. We've been doing work with Daniela Roos and Cecil. Daniela runs Cecil and all her team, both in Singapore on cars, but also in Amsterdam on something else. The mayor of Amsterdam came to us and wanted to look at autonomy in the city. Initially, looking at cars. But when you look at Amsterdam, the city has no roads. The city center is water. And so we said, why don't we do something else? Everybody's doing autonomous cars. Let's do something else. Let's do autonomous boats. We call them robots. What can you do with a robot? We can use a robot to move things around. You can use robots to move people around, to sense air quality, water quality. But think about robots that allow you to come together, connect, and do like a temporary bridge when you need it, or a floating stage, like a responsive dynamic architecture that can actually change based on necessity and use, which, by the way, some cities have been doing in the past in an analog way, but now you can do it in a different way. This was actually 3 years ago. We did the first prototype. Here you see different type of propulsion for the robots. This is a small robot, 1:4 scale. Here you can see, being tested in Amsterdam, symmetrical, very controllable. It can also move laterally. We told the mayor, even if the research fails, we'll open a toy company because everybody seems to have so much fun playing with this in the canals. Anyway, I'll show you, we had to look at all the data in the city, collecting data in real time from all the robots. This is actually how robots see a city. So how a robot looks around using LiDAR. Every second you got 300,000 data points. And when you combine them, you get this kind of full 3D representation of the city that you can also use to better understand the urban environment. Well, this is the data you get in, then you need to train the system. So this actually, we hacked the MIT swimming pool, as you see here. And you see the system uses a LiDAR, all the data to navigate, avoid different type of obstacles. Like here, this type of obstacles, a very complex type of obstacles. This is actually Wei, one of our postdocs, and our assistant professor. He got promoted after this. You can find this is one of the most exciting papers that came out of it. It's it's now being used a lot in the community. And here's actually Robot Today, which became just a company in Amsterdam. It was again a TLO collaboration, MIT, TU Delft, and and this is where it stands.
This is Lucy.
Oh, sorry.
The autonomous, zero-emission boat that operates on urban waterways, and she can change the way cities work. As congestion and emissions continue to rise, while cities continue to grow, the existing infrastructure of many cities struggles to keep up. rowboats offer a solution by moving road traffic to the water. By bringing passengers from A to B, or as an on-demand boat, taking you anywhere you want. And they can also help the city as a multi-purpose workboat. Take Kristen. She is equipped to collect household waste to free the streets from heavy garbage trucks. Rowboats are fully autonomous, so they navigate without a skipper and can operate 24/7. In order to sail by themselves, rowboats need to perceive their environment and recognize objects such as bridge pillars, floating objects, and of course, other vessels. The primary source of information comes from a LiDAR sensor, but rowboats are also equipped with cameras, GPS, and a digital compass. Rowboat's onboard computer combines and processes all of the data and runs the rowboat software so it can successfully complete its mission plan. After 5 years of development, testing and experimentation, we have now successfully enabled autonomy on the full-scale prototypes. Rowboat is ready for the next step. Join us and let's unlock the potential of urban waterways together.
And actually, Robot will be, that's Robot, the company, it will be premiered this year at the Paris Olympics, so it will be on the water at the Paris Olympics. So those are some of the things we've been doing with autonomy. You know, I don't want to I mean, there's many more projects I can show. I'll tell you just another thing, a company that came out, in this case from our design office, not from MIT, is the world leader in autonomy for robotic bartending. That was started more for fun and then it's exploded, so it grew out of its own all over the world. Final thing, environment. Environment in funnel is fundamental. We need to collect more and more data on the environment. So here we've been doing quite a lot of work, in this case starting from using data from cars, including autonomous cars. What you see there, the two little things are LiDAR, like the one we saw for robot. And then, the car today collects data from thousands of sensors. And the data can actually tell us a lot about the city and about infrastructure. So there's a paper, we explore how the car can be used as an ambient sensing platform, or also how we can use it in order to better understand different type of infrastructure. This is a bridge that collapsed in Southern Europe a few years ago. But but there's many bridges that collapse. Any structural engineer in the room, which bridge is this one? Tacoma Bridge, yes. The Tacoma Bridge, there was one of the first ones that was filmed collapsing, and actually helped to rethink how we design suspension bridges, because for the first time we could document what happened to it during wind and how it started resonating. But you all know this bridge, right? That's Longfellow Bridge, and we all go on Longfellow Bridge, and as some of you might know, just a few years ago, 5 years ago or so, then somebody looked at the bridge in detail, so it was about to collapse, and the bridge had to be rebuilt at a huge cost to the city. A monetary cost, I think it was a few $100 million, but also cost by separating the city, two sides of the city, for a number of years. And the reason for that is that today, if you want to monitor a bridge, you go two ways. Either you put sensors, as you see to the left, or you send people on the bridge for inspection. Well, believe it or not, today, if you want to monitor a bridge in this country, it will set you off $500,000 per year per bridge. So we'll never be able to monitor all the bridges in the United States. But what you collect when you monitor a bridge is actually what you can call like a structural fingerprint, which is mostly vibrations. And today we got many ways to measure vibrations. Our cars measure vibrations, our phones have accelerometers, gyroscopes, and also what you see there in orange is a professional accelerometer. So we asked ourselves, what if you could actually use all of that in order to measure the structural stability of bridges? And we decided to start with this bridge. You all know it, with the Golden Gate. And the reason is that the Golden Gate has been studied so much, is very well known and understood, that we basically can use it as ground truth. We can compare our data with the data which is collected all the time about the Golden Gate. So we started going back and forth across the Golden Gate with our car over 100 times. At the end, after 100 times, the San Francisco police got suspicious. So they banned us from... But then we had collected enough data, so you can see here the raw data. And then we analyze it, and well, that's a paper from last year. It turns out, or 2 years ago, it turns out that actually you can use all this data in order to understand the structural stability of bridges. And now we're doing this at a large scale using data from Uber and others. Imagine tens of thousands of cars moving across the infrastructure, and then it allows you to get a sense of the stability of it. And maybe it's not as perfect yet as it could be if you put sensor on the bridge, but then it's like triage we did during COVID. You do a first scan, and then if you see something, you can go there and just focus your attention on the places where you see that some problem might occur. We've also been using a lot of other sensors. This has been in Cambridge, putting instrumented garbage trucks and moving around the city. I will skip a bit the video. Again, when you look at this, then you discover interesting thing you didn't expect. With 3 cars, with 3 garbage trucks, we could actually cover all of Cambridge, go everywhere at least once a week. And then we say, how does it scale? If you put actually sensors, not like cities have always done, by using fixed sensors, but if you put them on movable things, how does it scale mathematically? And in this paper, we actually discovered this beautiful dependency. You see this kind of curve. It's very vertical at the beginning, then it's very flat. On the x-axis, you got the number of vehicles moving in the city. On the y-axis, you got how many streets you scan. It's so vertical. In New York, if you just put like a few dozen of sensors, then you can scan half of the streets at least once a day. This is in this case, it's actually once a day. The result was so beautiful. The curves are so perfect. I remember the first reviewer on PNAS thought we had fabricated the data. We actually had to share the real data to convince him that actually that it was true that actually this is a curve. And now people are using this in order to do deployments. So in order to simply put fixed sensors, you can put them on cars, and then you can use this curve in order to see how many you need in order to get a certain resolution over space and over time. And then with that, you can also look at how people are exposed to pollution. This was the first article that actually combined mobility of humans with air quality. Again, air quality usually is seen as something static, but the important thing is to see how your exposome is affected, which means it's important to see how you move through the day and how then you move through different pollution level. Here you can look at how other dimensions. Looking at trees, tree coverage. We're doing a lot of work on using CNN, deep learning, in order to analyze street view images. And we started by looking at. In this case, at the beginning, we started with image processing. Then we moved to, this was 5-6 years ago. Then we moved to CNN and to actually look at different things about trees and many dimensions of the city. You see it here. We open. In this case as well, to have a conversation with people. We created a public platform called Treepedia, where actually many cities can process Google Street View data and then do this kind of map of trees, something that otherwise you don't have. And the amazing thing was that we started getting calls and emails from, I would say thousands of people who said, I'm using the data in order to ask the mayor to plant more trees, or ask, why my neighborhood doesn't have enough trees compared with other neighbors. So sometimes when you just share data, that's another good way to start feedback loops with the city. And again, you can get all of this, you analyze it. Today it's getting easier and easier. You take images and you analyze and you detect a lot of things there, and there's a bunch of papers. We've also looked at other dimensions, not only trees. Here you see house prices. This is the latest paper. We looked at kind of social city profiles in cities by analyzing Google Street View data. 2 very quick things to finish. We've been looking a lot also at biology in cities. Who knows what this map is? Any thoughts? This is a famous map. It's called John Snow Map of London. It's a famous map because that map, by mapping cholera cases and wells, they actually, at the time, understood how cholera is transmitted. And that was done by John Snow by looking at this part of London and again looking at all the wells in cholera cases. At the time, people didn't know that cholera was being transmitted by water, and by actually doing the map, they realized that. And so we started a few years ago to say, what if you can actually look at water in the city, and especially wastewater, and then together with people at the Broad in biology, we started sequencing wastewater in order to look at bugs and other things. We designed a little robot to go into sewage. Here you see it, some images. It's a second iteration, the small robot, and this data you get. The data you get from Cambridge. Here you see the network, the sewage network in Cambridge, so you can look at the different catchment areas. And here's actually the information we started collecting. And here are some of the some of the papers, but also out of this, then the two people you saw in the video started a company, Biobot, and Biobot was actually the main company doing. This was just before COVID. It was one of the main companies during COVID to do wastewater analysis all over the United States in order to look at different things, including the presence of COVID. And if you know where COVID is, for instance, you don't need to shut down or do lockdown in an entire city, but you can actually be much more precise. And also you can look at epidemics before they happen. You can look at the signal even before people have symptoms. So to finish, again, we enjoyed a lot looking at these kind of less known aspects of our cities. So wastewater, sewage, in this case, actually waste. Today, if you look at this computer here, you know everything about it. Every chip in that computer, you know where it was produced, how it moved on the planet, how it became this machine. A few years from now, you stop using it, you sell it, at some point somebody will throw it away, and then you know very little about it. Sometimes actually electronics ends up where it shouldn't, like this. So our initial idea a few years ago was, what if you could design a little tag to put on trash and to follow trash as it goes away through the sanitation system of the city. We couldn't find anything off the shelf, so again we teamed up with C-Sail and we designed almost like a miniature cell phone with a difference. Your cell phone is designed to send a lot of information for a very limited time, 1 day or 2 days. In this case, it's very little information, just position for a long time, months or even years. And here you find some of the papers. This was the first deployment we did in Seattle. We put a little tag on different types of trash, from electronics to banana peels. And after tagging all of them, we started following them. So here you see 3,000 tags, the day of deployment. After a few days, you see some of the main landfills next to Seattle. And actually a big surprise, how far stuff started to travel. Sometimes in a crazy way. Look at the trace that went all the way to Chicago, changed its mind, and went back to California. We thought the Farewell Symphony was the right music. So then, more recently, we actually did a global deployment just on e-waste. The first deployment was in Seattle, 3,000 tags, only the United States. And then we looked at global flows of e-waste. In this case, what you see here is from the United States and flows all across the planet. Some traces are legal traces. Some of them are not. But again, the idea that data, especially if you make it public, this became also a PBS documentary. If you make it public, it can help the integrated feedback loop, and perhaps to fix some of the loopholes we got in this case, in our legal and environmental system. But when we were doing this, we discovered something else, and it was totally unexpected. That happened actually on the MIT campus. That happened when a burglar came to our lab at MIT, and this poor guy stole a lot of things, including tags and computers that tell you where they go. And this is what happened. Thank you.